Okay, today we're going to look at reversible reactions and how they lead to equilibrium. So first, what do we mean by a reversible reaction? Well, a reaction that can happen in both directions. Okay? So we saw that we could put hydrogen and oxygen together and make water. We got energy. That's where we got that pop out of the test tube. But if you remember, I made the hydrogen and oxygen by separating water, by putting energy in. Now, it's pretty lazy. The scientists are pretty lazy. They don't want to have to write the same equation twice. So they're just going to take that equation and write it once and change the arrow. So all they did was they took the arrow and they turned it around. The top half of the arrow. So they took an arrow like that, and they took the top half and left the top half alone, turned the bottom half around, you get a reversible arrow. Okay? So, well, that means we have to change our definition of reactants and products. Because is hydrogen a reactant or a product? Well, it depends on, if you go this way, it's a reactant. If you go that way, it's a product. The pen is not working real well today. We'll have to fight that. Okay? Fight it. So, we are now going to have to change our definition of reactant products so that reactants are the things on the left and products are the things on the right, because we can't say what you started with or what you ended with, because if I start with all water, I can turn it into all hydrogen oxygen. If I start with hydrogen oxygen, I can turn it into water. So reactants and products, we have to change their definitions. Okay. And if you have a reversible reaction, if there's a reversible reaction, eventually you will reach equilibrium. So let's look at those rates and see what's happening. Okay. When I first put the reactants together, the reactants are going to run into each other. And if they run into each other, they have a chance of colliding hard enough to make a product. And so the forward reaction is going to start, but there's not going to be a reverse reaction. Okay. But as the forward reaction proceeds, the reactants are going to turn into products. Well, if you use up the reactants, the concentration of the reactants goes down, so that reaction slows down. And the products build up, so the reverse reaction speeds up. The concentration of my products, I start off with none, then I have a little bit, then I have more, then I have more. And it's this interplay right here that the forward reaction is slowing down and the reverse reaction is speeding up, is going to lead us to equilibrium. So I found a site that let us put numbers with this and graphed it so we can see what we're talking about. So I went to, it's Cal Poly Pomona. Okay, so they have the site for kinetics and equilibrium. Kinetics, how fast equilibrium is tied closely to kinetics. So let's look at the kinetics graph first. Okay, so what this graph is going to do is, in the table, I pick what are the chances that A is going to turn into B. And my lowest chance is 20%. So what that's talking about is what percent of the collisions are going to be hard enough to make this reaction happen. So I pick 20%. And then it asks me to fill in the table. So A has 100, and if 20% turn into B, then 20 will turn A to B, and I'll have 80 of A and 20 of B. So I started off with no B and some A, and in my first amount of time, the concentration of A went down, the concentration of B went up. Now when I go to take my 20%, I got to take 20% of the 80 A's I have left. So 20% of 80 is 16. Okay. So my concentration of A is going down, but notice it didn't go down as much. The first time it went down 20, the next time it went down 64, or right down 16. So the amount of A disappearing is slowing down. The forward reaction is slowing down. Now I take 20% of 64. 20% of 64 would be 12.8, so that's 13 when you round. Now I'm at almost 50-50. And I got to take 20% of the 51, that's going to be 10. You'll notice that the amount of A changing every time goes down more and more, and the amount of B increases all the time. And 20% of 41 is 8. 20% of 33 is 7. 20% of 26 is 6. Oops. Oops, sorry, it's got to be a 5. Got to round down, sorry. And then 4. And then 3. 2. Oops, actually, it's only 1. Oh, so, no, it's number 3, I'm sorry. 2. 2. 2. Oh, sorry, got the 1. And it's just going to be 1 from here on out until it's all gone. So, looking at the graph, the amount of A decreased over time and the amount of B increased over time. And if you look at the pictures, I started off with all red stuff, I ended up with all blue stuff. Okay, so the red line is what happens to the reactants, and the blue line is what happens to the products. Now, let's see what happens if we try that when it's a reversible reaction. So the graph looks the same, the table looks the same, except now I got 2%. So let's pick 20% changing from A to B, and a different percentage changing from B to A. So maybe B comes apart easier than A does. So I'm going to pick, just to make the math easy so I can do it in my head, 50%. So I start off with 100 atoms of A and 0 of B. So in my first time frame, 20% are going to turn from A into B. So 20% of 100 is 20. And 50% of B's are going to turn into A's. Well, since there's no B's, 50% is 0. And you'll see that this first step looks just like the first step on the kinetics one. The concentration of A went down, the concentration of B went up. But here's where it's going to be different. Now I take 20% of 80 at 16, but now I need 50, but instead of none turning back, now 10 are going to turn back into A. 50% of those are going to turn back into A, so that's 10. And if you'll notice, the next step, the slopes of the lines changed. A became less steep. It's slowing down. B is speeding up. Before there was none changing, now there's 10 changed. Now 20% of 74, 14.8, that's 15. And 50% of 10, or 50% of 26 is 13. Then 20% of that is 14. And 50% of 28 is 14. And that's 14 again. 14 again. And I could just type 14s forever, because it's always going to be 14. They're not going to change. That 14 turn in from reactants to products, 14 turn in from products to reactants, and it's going to stay that way forever. Now the reactions don't stop. A is turning into B just as fast as B is turning into A. And I will reach a stable amount, okay? And that stable amount is really determined by that percentage. When I'm stable, I have 28 B's and 72 A's. That's 0.39. If you think about my percentage, the percent change from A to B was 20. Change from B to A was 50. And that's 0.4. And the reason why they don't come out exact is because of rounding. Okay, it's back, our numbers are too small to get it perfectly. But now, if I had started at a different place, I would have done the same thing. The A would have gone down, the B would have gone up, but they would have run into each other a different part. So that's how you end up with a reaction that's running but not changing. So the forward reaction gets used up, so it slows down. The products build up, so the reverse reaction speeds up. Eventually reach a point where the reverse reaction is going just as fast as the forward reaction. So you're turning products into reactants just as fast as you're turning reactants into products. So everything's going to stay where it's at. That's dynamic equilibrium. Equilibrium means balanced, staying the same. Dynamic means moving, because the reactions are still running. So the reactions are still running. Nothing's stopped, but they're just running in the opposite directions at the same rate. It's kind of like a dynamic equilibrium is running on a treadmill. You're moving, but you're not going anywhere because you're moving forward just as fast as the treadmill's going backwards. So what's true then is that the rates are equal. How fast they're going is equal. The rate of the forward reaction equals the rate of the reverse reaction. Not the amount of stuff, the rates. Okay? They're constant. They stay the same. The concentrations stay the same. But the reactions are still running. I'm still using up reactant. I'm just making it as fast as I use it up. And that's dynamic equilibrium. You talked about this last year in biology as homeostasis, where everything was staying still because everything you did was balanced. And so what we got to here is we reached a point where everything wasn't changing, and that's called an equilibrium position. How much reactants and products you have at equilibrium. So our equilibrium position here would be 72 A's and 28 B's. And we can tell you where the equilibrium position is based on how we draw the arrows. So you see on this first set of arrows, I'd left the top one small, made the bottom one big. That means the reverse reaction is faster than the forward reaction. And if that's true, when I'm done, if the reverse reaction is faster, I'm going to end up with more reactants than I do products. And I show that with the arrow. The big arrow says reactants are favored, and the other one is obviously, if the top arrow is bigger, that means the products are favored at equilibrium. So if they change the size of the arrow, they're telling you which way goes faster. The bigger arrow is the direction that's going faster. The bigger arrow is going to point at the one that's favored. Now, we talked about catalysts speeding up reactions. What effect do they have? Well, they actually speed up both reactions the same amount. So if you're walking on a treadmill, you don't go anywhere because you're going just as fast as the treadmill. If somebody turns that treadmill up to high speed, you still don't go anywhere, but you have to run faster. Okay? Well, the catalyst is the effect of you turning up the treadmill. You go faster, but you don't get anywhere. You end up in the same spot, only faster. Okay? So that's the idea behind equilibrium. And now we can measure where we're at equilibrium. So that ratio. Okay? And what we measure are the concentration of the product and reactants, the parts that are constant. And we can write a constant that will tell us where the equilibrium position is. It'll tell us what ratio you're going to have when you stop. But we're going to call that the equilibrium constant. Capital K means constant in science, EQ for equilibrium constant. And the way you calculate the equilibrium constant is you take the products over the reactants, and those coefficients are the ones from the equation, and you raise them to that power. So that's the square brackets means molarity, moles per liter. So I'm going to take molarity of the product, we take the molarity of the product and divide it by the molarity of the reactant. So it's products over reactants raised to the power of their coefficients. So let's write some equilibrium expressions. So if I had the general equation, this is as general as you can get. I've got two reactants, two products. The lowercase is the coefficient. The uppercase is what the stuff is. So if I had 2H2, why won't this let me write, plus O2, 2 would be the little a, H2 would be the big A. And now, so we said we're going to put the products. The products are C and D. Won't you work? Products are C and D. They go on top. And they're raised to the power of their coefficient. And the reactants go on the bottom. Raised to the power of their coefficient. If you look back here, we had that ratio here, down at the bottom, stable A, stable B. Okay? And those ratios were about how much stuff you had, but they really were tied to how fast what chance you had of them reacting. Okay? So that equilibrium constant is really based on the nature of the reaction, and that equilibrium constant is constant. Okay, so let's write some equilibrium expressions for some stuff. I see I'm fighting the screen right now, so we'll see what we can do about that. I may have to pause this so we can try it someplace else. Okay, so how would you write the equilibrium expression for this? This is how you make ammonia. Well, the equilibrium expression for this would be, come on, it will not write. I don't know what's going on. Give me a second here. I'm going to pause and I'll be back with you in a second. So, back here we got the equilibrium constant, KEQ, is going to be equal to products. The products are H2 and N2. No, they're not. Those are the reactants. The product is NaH3. The most common mistake is putting the wrong thing on the top. Then we got H2, and we got N2 as my reactants on the bottom. I want to put them in square brackets. I'm going to pause again. Okay, so we got to remember to put square brackets around these. Okay, and then the only other part is we got coefficients. That's a 3, that's a 1, that's a 2. So the 2 is on H3, so that's squared. The 3 is on H2, so that has to be cubed. And N2's got a 1, raise the first power. And if you calculated those numbers, it would always be the same when you got to equilibrium. Equilibrium constant. Let's try another one. Maybe I get the pen to work a little easier. Oh, the one we talked about here. How would we write that equilibrium constant? Okay, Q equals products H2 and O2 of reactants H2O. Need square brackets to say I'm going to measure them in molarity. And then I have to put in the coefficients. There's a 2 on H2O, so I square H2Os. There's a 2 in front of H2, so I square that. There's a 1 in front of O, I do that. And that's the equilibrium expression for water making hydrogen and oxygen. So once you write that equation, you can calculate it. And the equilibrium constant is only affected by temperature. Temperature changes the equilibrium constant, otherwise it's constant. Okay? What I call it a constant is unless you're at a different temperature, it stays the same. So, calculate the equilibrium constant for our equation. If I've got this many moles, this many moles, and this many moles in a 2-liter container. So the KEQ equals, I always write the equation out so I know what numbers to stick in. The number for NH3 on top, H2 on the bottom, N2 on the bottom. I want them in molarity, and I need the NH3 squared. I need the H2 cubed, and N2 to the first power. Now I can stick in the numbers. I've got 0.25 moles of NH3, but 2.25 moles divided by 2.0 liters is 0.13 molar. So 0.13 molar squared divided by H2. There's 0.1 mole of H2 in a 2-liter container, so 0.1 mole divided by 2 liters is 0.050 molar. I need to cube that. And then I got to figure out the concentration of the N2. And the N2 was 0.15 moles. If I divide that by about 2 liters, I get 0.075 molar. Okay, and we push those buttons. Okay, so now we just have to push the button. So 0.13 squared divided by 0.05 cubed divided by 0.075 equals, and with 2 sig figs, I get 1800. And what kind of units do I have? Well, this top is molar squared. The bottom is molar cubed times molar, that's molars to the 4th. So my actual answer is 1800 molar to the -2nd. Yeah, every time you do this, you're going to get bizarre units. Okay? Because you're always going to have powers of molarity on the top and the bottom. So you always have to, different units for every time you do the problem. You have to figure them out every time along the way. Okay? So that's what your homework will have on it. It'll have you write some equilibrium expressions and calculate some equilibrium values. Okay? We'll talk more about equilibrium tomorrow. Have a great afternoon. See you online today, if I haven't already.